All right, in this video, I'm going to introduce the free body diagram. So the free body diagram is the diagram that we need anytime you're going to work any problem that uses first or second law of motion. So anything with forces, we need a free body diagram in the same way that anytime we're working with constant acceleration, we needed our interval diagram. So I'm going to go through, I have kind of these strategy points listed out here, but I'm just going to really talk through those in the context of the examples below. The biggest thing we want to focus on when we do a free body diagram is just remembering that we are going to identify some object. So we're only going to have a single object or system when we're doing a free body diagram. So we need to know what that is. And then we're going to think about all the forces that are acting on that object. And we want to remember that every force we identify is acting on our object needs to have an agent, right? If I can't identify an agent, then there is not a force. All right, so let's look at example 1A. So we have an elevator suspended by a cable descending at constant velocity. So first thing is we want to identify the object. So I'm going to say the object I care about here is the elevator. And then I'm going to make just a quick little picture. So here's my elevator. Maybe I have some people in here. Here's my little people. I've got an elevator suspended by a cable. So I've got my cable drawn on there. And then it says our velocity is constant. So if my velocity is constant, I know my acceleration is 0. I'm just going to make that little note here. Whatever our object is, that's going to be our dot, right? So there's my particle. There's my elevator, which is the object. And then we want to do this here. Then we want to just make a little circle around our object. And so as we're getting started, this is a really good tool. Didn't take me very long to make that little circle there, right? And that is going to help us identify all our forces and make sure we have everything we need to include. So when I identify my forces, we first can think about our long range forces. So we always have the gravitational force. So I'm going to go ahead and throw that one in here, and that is F sub G. So gravitational force is always directed straight down. So I always know what direction it's going, and it's always present. So that one's an easy one, right? So that's a long range force. It does not cross this little bubble or boundary that I drew here. So it's the only force that we're going to be working with this semester that I can't visually see in my picture. All right. The next thing we do once we have that one is I want to see anything that is crossing that boundary that I made. So anything that's crossing the boundary is going to be a contact force. So I only have one thing in here. So in this case, the only thing crossing the boundary is that cable, and the cable is like a rope or a string. So that's going to be a tension force. And so that tension force, if I think about how it's acting on the elevator, it's pulling back up on the elevator. So that's going to be going this direction. And I'm going to label it with a capital T. In this case, so I did draw a bunch of like people in there. The people don't matter, right? Because the people are internal. So I don't want to put any forces on anything that is inside of my object. Those are going to be what we would consider internal forces. And we'll talk about why they don't matter in the context of what we're doing here in just a little bit. So for this particular one, I have just gravitational force and the tension force. These are the only two things. I've got the one long range. I only have one thing contacting my elevator. And so this would be all of our forces. It is a diagram and forces are vectors. So I do want to also include a coordinate system. So I'm going to just I'll say that y is positive going up. So I'll do I'll just do this here. So there's my y-axis, and I have my y direction going up. I can also just over to the side over here, just say y is positive going up. The other thing that will be helpful, especially as we start working through problems, is to say what your acceleration is if you know anything about it. And so in this case, it said constant velocity. So AY is equal to 0. So in your free body diagrams, you will want to indicate what you know about the acceleration, because that's going to connect us to our starting equation. So complete free body diagram for this one. I have two forces. My acceleration is equal to 0, and then I've got a coordinate a coordinate system indicated as well. All right, let's look at the second one. I have a car traveling on an icy road, sliding into a snowbank. So I'm gonna make just a little, here's my car, here's my road, and then here, this is my snowbank. Okay, so I've got this situation. So we are gonna be interested in, I'm gonna say the object is the car. And so make a little dot here for my car. I'm going to put a little circle here around the car, so indicating my object. So we always have the gravitational force. So I'm going to go ahead and throw that force vector in here, always directed down. Then I want to think about any other points of contact, right? So what are things that are crossing that boundary that I made, the little bubble I made around my car? And so we have two things. We have the road here is crossing that boundary, and then I have the snow, what was that? A snow bank that is crossing the boundary. So I want to think about the ground. So the car is on the ground. That means that ground is exerting a normal force up. So when I have a surface, I'm going to have that normal force. So that's N pushing back upward. And then the snowbank, if the car is moving to the right, hitting or contacting the snowbank, then the snowbank is going to be pushing back in this direction. I'm just going to call that the force of the snowbank. And so again, I think I mentioned earlier, it's good to always recognize what the agent of each of these forces is. So the agent of the gravitational force is the Earth. The agent of that normal force is the surface of the road. That's the contact, that's the thing exerting the force, pushing back up on the car. And then the agent of the snowbank force here is the snowbank itself. So the snowbank is contacting the car, it's exerting a force on the car. So I have three forces here. And it said it was an icy road. So because it said an icy road, I'm not going to include friction. If we had friction, then I would put that in this direction, right? So if my car is moving, I guess I could put my little, I could say the car is moving in this direction. If I had friction or if it was not an icy road, we would assume that we have friction. And so I would put that in the direction opposing motion. All right, I have all the forces. We need a coordinate system. So I'm going to throw that in here. I can just say, let's say this is X and this is Y up here. And then we want to think about our accelerations. They didn't explicitly say anything about, constant speed or anything like that. So I'm going to just use what my diagram tells me. And what I might know about a car traveling on a road. So if my car is traveling on a horizontal road, then I should be able to recognize that my a sub y is equal to 0. So if I'm traveling on a horizontal road, then my car is not going up or down, right? It's not moving up in the vertical direction. It's not going down into the road. So there's no acceleration. There's no change in direction or speed in the y direction. So I'm going to say my a sub y is equal to 0. From this picture, I'm going to know that my a sub x is directed this way. So I'm going to be able to tell that due to the fact that I have an unbalanced force. So this is connecting us into what we'll be doing next. That if I have an unbalanced force in that x direction, then I'm also going to have an acceleration in that direction. And that probably should make sense also because I know that my car, if it's going into a snowbank and it's slowing down, right? Then if I do my little motion diagram, it's going to do this. And that means I must have an acceleration back in this direction. Okay, number 3, or I guess C. So C, we have a brick falling from the roof of a 3-story building. So here's my little building. Here is a brick and the brick is falling. So I'm going to put a V this way. All right, so there's my object. So object is the brick. Okay, and then here's my dot that we're going to use as our particle model. So I circled that brick and there's nothing contacting. There's no contact forces here, but we still do have the gravitational force. So I'm going to put that one in here. So in this case, if I do a coordinate system, I'm going to say y is positive going down. We should know that we would have an acceleration, right? I'm going to have an acceleration in the y direction that's going down. And actually, we know what that acceleration is from our free fall type of problems. We know that this actually is going to be equal to G, right? So this is just a free fall situation. In their free fall situation, the only force that is acting is that gravitational force. All right, last one here. We have a rocket that is launching straight up. So here's my little rocket. It's got some gas particles coming out the bottom. All right, so our object is going to be the rocket. And we'll put a little circle thing around our rocket. And it says air resistance is not negligible. So because of that, I'm going to put in like some particles here, right? These will be all my little air particles. So we'll make our little dot. There's my particle. We have our gravitational force is present. I've got our air particles. So as the rocket is going up, then the air particles are going to be pushing back. So it's kind of a contact force. So we're going to have a drag force. I'm just going to set this right next to that gravitational force. So they're headed in the same direction, directly down. And then we also have the thrust, and the thrust is going to be opposite of the direction that that gas is expelled, right? So if the gas is going out this way, then we're going to have a thrust force up this way. So F thrust is going to go in that direction. All right, so I need a coordinate system here. So we'll just say Y is positive going up. If the rocket is being launched, it should be increasing in speed. So I'm going to say my acceleration in the Y direction is in the upward direction, that direction of the thrust force. Okay. All right. So this is our starting point for any type of problem that is going to involve forces. So I need to identify my object. We're going to represent that as a particle. Then I want to think about all the forces that are acting on the object. So gravitational force always present. And then I can use just sort of circle around my object to identify any of the contact forces. And then I just want to label those in the direction that they're pointing with the tail of the forces at the particle itself.